Today we're going to be talking about rates and equilibrium. So we've been spending the whole year on chemical reactions, but what really is a chemical reaction? So a chemical reaction is a process that involves the rearrangement of atoms, something you already know. The law of conservation of mass states that mass is neither created or destroyed, meaning our mass has to remain constant, but it can change forms. So when we balance a chemical equation, what we are doing is that we are maintaining the law of conservation of mass. It is explaining how the atoms are rearranged. If you need a refresher on balancing chemical equations, I recommend you go back and watch that lecture video, but it should be a skill that you still have. So why are there double arrows in this reaction? As we've learned before, that means this reaction is reversible, meaning it can go in the forward direction or the backwards direction. Reactions can be reversible, meaning the products can rearrange to form the reactants, and then the reactants can rearrange to form the products. It can go either direction. So how chemical reactions occur? It all kind of boils down to collision theory, which states the molecules must collide with enough energy and in the proper orientation in order to react. Do all reactions require energy to occur? Yes. Energy is required for molecules in order to collide. They have to have some sort of energy, or otherwise they'd just be sitting in one place and would never collide with each other. This brings us to the activation energy, and this is the minimum energy required in order for the chemical reaction to occur. High activation energies slow the rate of reaction because they have to have so much energy in order to occur. It's going to take a long time to get that much energy. Meanwhile, low activation energies speed up the rate of reaction because it doesn't take very much energy to happen, meaning that reaction is going to happen a lot quicker. So what do we call a reaction that absorbs energy, meaning it takes in energy? We call those endothermic reactions. And what do we call a reaction that releases energy? We call those exothermic reactions. And in this picture here, you can see what we are talking about in regards to collision theory. These two atoms are colliding with each other, and when they do, the chemical reaction occurs, forming a new substance. So what about the energy in reactions? So once the reactants have gained enough energy, that activation energy, they are considered to be the activated complex. In other words, the activated complex is the reactants with a whole lot of energy. After the activated complex state, the reactants rearrange to form the products of our chemical reaction. This brings us to a new vocabulary word for you, which is enthalpy, and this is the change in energy in a reaction. So the difference between the energy that we started with and finished with. And this is represented by delta H, where you know by now that the Greek symbol delta means change in, and then we have H, which is enthalpy. So endothermic reactions are going to have a positive delta H and will feel cold to the touch, while exothermic reactions have a negative delta H and they are going to feel hot to the touch because they are releasing energy. Here are two different diagrams for you for our two different types of reactions. In this first reaction here, you can see that our energy of the reactants to start with is very low, and it finishes with a much higher energy of products. The difference between the product's energy and the reactant's energy is considered to be delta H. The difference between the energy of reactants and the very top of our curve is the activation energy, with the activated complex being at the tippy top of the curve. Now in this reaction here, since our energy of our products is higher than our energy of reactants, we know that this is an endothermic reaction. Energy was absorbed, and it has a positive delta H because it's energy of products minus energy of reactants. Meanwhile, over here, we have all of the same things, except we have our energy of reactants starting up high, with our energy of our products being very low. Energy of products minus energy of reactants is still going to be delta H. the energy of the reactants to the activated complex is still going to be our activation energy. But in this case, this is an exothermic reaction. Delta H is going to be negative, and energy is going to be released. So this brings us to two things we've briefly touched on, but now I want to talk more about, which is catalysts and inhibitors. So catalysts are a substance that speeds up a reaction without being consumed. They are not considered to be a part of the chemical reaction. They're like a helper, but they aren't actually participating. So how do catalysts work? They lower that activation energy. They make the curve lower. So now it's going to take less energy to make that reaction take place. This means they can increase the rate of the forward and the reverse reaction. An example of a catalyst that you should already be familiar with from biology is an enzyme. They are biological catalysts that speed up reactions in our bodies. And more specifically, enzymes are a large molecule, usually a protein, which catalyzes biological reactions, which are reactions in your body. You spend a lot of time learning about those in biology. An inhibitor is essentially the opposite of a catalyst, and it's a substance that slows down a chemical reaction without being consumed, and it is not a part of the reaction either, so you wouldn't see it written as a reactant or a product. They are going to decrease the rate of the forward and the reverse reaction. A diagram for you. So in blue, we have our chemical reaction without a catalyst. It goes along. Activation energy, activated complex goes down to products. With a catalyst, you can see that we start in the same place and we end in the same place, but our activated complex is much lower, meaning our activation energy is a lot less. We'd still calculate delta H the same, products minus reactants, so this reaction would still have the same delta H, but it would have a different activation energy only. So let's talk a little bit more about enthalpy. So enthalpy is the amount of energy transferred between the system, the reaction, and the surroundings, the environment that we live in. So delta H is the products minus the reactants. If we have a positive delta H, we know that our reaction is endothermic, meaning more heat goes from the surroundings into the system. And we can also have a delta H that's negative, which makes the reaction exothermic. And this means that more heat leaves the system and goes into the surroundings. So it's giving off heat as opposed to taking in heat. Keep in mind that energy is not created or destroyed, just transferred between the system and surroundings. This is the law of conservation of energy. So just like mass, energy isn't created or destroyed, it's just moving around to different locations. Let's think about burning a match as our example. So we have our unlit match. That is our reactant, and it's starting up here. This is our system, which is the match. Then we have our surroundings, which is the area we light the match in. So we have the energy required to start the reaction. This is when you strike the match on the side of the matchbox. Then the match is going to burn up, and it is releasing all of that heat. It feels warm, right? That's what fire feels like. That is it releasing energy into the surroundings. When it's all done, we have our burn up match as our product. We could take our product and subtract our reactant, and that would be the delta H, the difference in energy. And since it gave heat off to the surroundings, it's going to have a negative delta H, which makes it an exothermic reaction. So this brings me to Hess's law. So Hess's law states that the enthalpy of a whole reaction is equivalent to the sum of its steps. And that sounds really scary, but it's really not. So essentially all reactions have a delta H with them. Products minus reactants, nothing scary there. And most substances have a delta H that is known. Scientists out there have already calculated it. They know what it is. Delta H is usually measured in the unit of kilojoules, abbreviated kJ. And the change in enthalpy is actually caused by bonds breaking and bonds forming, depending on how high or low energy those bonds are, or what is determining whether it releases or absorbs heat from the surroundings. So you can calculate Hess's law, and it's actually really easy, and I know you can do it. So the official formula is delta H equals sigma delta HF products minus sigma delta HF reactants. And that seems really scary, I know. And you're like, Miss Hinkson, I don't know what that means. But it's really not that bad. What does it mean? That just means that delta H is the sum of the enthalpy of formation of the products, meaning we look at our products, we have known delta H values for all of them, and you add them all together, minus the sum of the enthalpy of formation of the reactions. So we know the H values for all of our reactants, we add them all together, and we're just going to subtract those from their products. Something you do need to know, though, is you need to look at the coefficients in the chemical equation, meaning you have to balance that chemical equation first if it's not balanced for you already. And you must account for all of those substances. So keep in mind, if it's 2H2O, that means you have twice as much water, and you need to account for that. So you're going to use the coefficients to multiply. Something to be aware of is be careful adding and subtracting negative numbers. Your choices are to use parentheses, like I did up here in my example, or to distribute the negative, which I'm going to be showing you in some upcoming examples. So let's take a look. A typical kind of Hess's law question would be like this. When methane is burned in oxygen, carbon dioxide and water are produced. And there's our chemical equation, and I was nice enough to already balance it for you. You are asked to calculate the change in enthalpy when methane is burned using the following, and you're given a table. This is the kind of question you can expect to see on quizzes and tests. Now let's see how you'd solve that. So once again, this is the equation that we were given before. I've changed the colors so we can keep track of things. I put my reactants in blue and my products in red. And then this is the same data table you were provided in your previous example. So remember what I said before, delta H is going to be your products minus your reactants. So I have my products over here and my reactants over here. So that means I'm going to have products minus reactants. Now, like I mentioned before, you could keep the parentheses if that works better for you, or you can distribute the negative, doesn't matter to me. So you could also think about it as CO2 plus 2H2O minus CH4 minus 2O2. All I did was distribute the negative inside my parentheses. Either way, it works the same. Then we're going to just plug in values from the chart. So I see that CO2 on my chart is negative 393.50. I'm going to add that to 2H2O, so that means I have 2 times the amount of H2O from the chart, minus my CH4 from the chart, and then minus my O2, which keep in mind I had 2 O2s, but since O was 0, 2 times 0 is still 0, so it doesn't matter. I punch that all into my calculator. I could simplify the H2O down ahead of time if I wanted to make it easier, or just enter it all in my calculator, depends on what you prefer. And I would have come out at the end with a delta H that equals negative 890.36. See, really not that bad. So let's try another example. I want you to try this example on your own and pause this video and come back when you're done to see how you did. So this time you're told to use the standard enthalpies of formation table to determine the change in enthalpy for the following. NaOH plus HCl produces NaCl plus H2O. So try this one on your own, follow the example we just did, and come back when you're done to check your answers. All right. So once again, same formula, same table, just rearranging it. You still should have done products minus reactants, which would have worked out to NaCl plus H2O minus NaOH minus HCl. I found my values from the table, punched them all into my calculator, and you got the correct answer if you got a value of negative 177.83 kilojoules. Don't forget that unit at the end. How'd you do? If you got this example right, you're probably going to be a Hess's Law master. If you got this example wrong, take a look at what you did and consider coming in on Monday or Tuesday to ask me some Hess's Laws questions over my video chat. Have a great day.